to avoid conditioning on some observed covariates in the hope of obtaining an unbiased estimator because of phantom but complementary imbalances on unobserved covariates is neither Bayesian nor scientifically sound, but rather it is distinctly frequentist and non-scientific ad hoc. His position is essentially that this stuff is not useful. Well, Rubin, your method would probably tell us to adjust for Z2, but the backdoor criterion tells us that this would create a collider bias, and you cannot remedy the bias because Z1 and Z3 are unmeasured. Okay, so Clash of Titans. So there's this competition that's still kind of ongoing. So on one hand, we have the Rubin causal model. So this is attributed to Donald Rubin, who's a very famous statistician from Harvard, who in the 70s rediscovered this notion of potential outcomes that sometimes you kind of see them named as counterfactual values. And he sees the goal of causal inference to kind of infer these counterfactual values and compare them. So if under a treatment, the counterfactual value would be different than under a control, then we can say that there is a treatment effect. And just to give you a little bit of the flavor of what we can expect. So this is a quote from him in 2009, I think. So to avoid conditioning on some observed covariates, as Pearl suggests, in the hope of obtaining an unbiased estimator because of phantom but complementary imbalances on unobserved covariates, is neither Bayesian nor scientifically sound, but rather it is distinctly frequentist and non-scientific ad hocery. So we already see the kind of language that he's using. And sorry for messing up. I haven't read out loud in English in a long time. And on the other side, there's Judea Pearl. So he's a computer scientist. So he kind of has two phases in his career. The first one was very much AI, computer science, engineering based. But he kind of stumbled upon causality through that research. And then he kind of devoted the second leg of his career to studying causal inference and kind of building bridges with different disciplines, most notably epidemiology. And his framework, we can kind of summarize it as the framework of structural causal models. And for him, the core task of causal inference is estimating what happens to a system of variables when you perturb them through an intervention. So you have a system of variables, you give a treatment, he sees it as a perturbation of the system, and you kind of want to see what happens to certain outcomes when you do that intervention. And to get a bit of a flavor of what he thinks, he says, Rubin will do well to expand the horizon of his students with some of the tools that his admirers now deem illuminating. So the potential outcomes theory that comes from the first guy, Rubin. So in this framework, we start with a population. Let's say we have n units. It can be people, it can be anything. And let's just forget issues about sampling. Let's just assume we have the whole population and there's no sampling uncertainty. And each unit is characterized by a set of covariates, right? So a unit essentially is the kind of ensemble of its characteristics. So its age, its sex, or whatever other variables that kind of are relevant to the problem. We have two possible treatments. So a control or a placebo that we will label 0, and a treatment that we consider like the active treatment that we will label 1. And we model the treatment actually taken by a unit as W, and we just subscript it with I to say, well, this is the treatment taken by unit I, right? So it can be 0 or 1. And the counterfactual treatment, so the one that we didn't observe or the one that the unit didn't receive in real life, never really happened. So we say that it's counter to the fact, and a simple way to denote that is just say 1 minus W. So when W is 0, 1 minus W gives 1. But when W is 1, 1 minus W gives 0. So it kind of always mirrors the counterfactual treatment. Related to that, so each unit has two potential outcomes. So we assume that these values kind of exist in this metaphysical sense, like, oh, if we give the control to a unit, his blood pressure will be this value. If we give the treatment, his blood pressure would be this value, right? And we just put symbols to denote that. And the variable we observe, we can write this rather like complex looking equation, but it's just basically saying that if we give the treatment to a unit, we will observe his outcome under treatment. And if we give control, we will observe his outcome under control. But we cannot see the counterfactual, right? We would have to duplicate the world and just change one small detail to be able to compare, right? So that's kind of sometimes called fundamental problem of causal inference. We don't have access to these counterfactual worlds, but we can use some ingenuity to kind of estimate what happens and then compare. And that's kind of the whole business of this Rubin causal model or the potential outcomes framework. Yeah, so this is the missing outcome. It's the same thing. We just write it with a complex equation, but the principle is rather obvious. And then the comparison between, so for unit I, let's say I am unit I, if we want to determine if there's a causal effect, we would compare my two outcomes in these counterfactual worlds, and we can do that additively with just subtracting one from the other. We can take ratios, we can take log transformations, we can do whatever we want. But the problem is that we don't have access to these values, so we kind of have to use techniques to estimate this. This is kind of like the meat and bones and the abstract part. So this might be a bit more complicated, but in this framework, what's important is to model the assignment mechanism or the treatment assignment mechanism. And this is basically saying, well, there's a certain probability that a person receives either the treatment or control. And that probability, so again, we use math notation, but the notation is not really important, right? So the probability of seeing a certain distribution of outcomes of treatment assignments. So Andy gets control, I get active treatment, et cetera, et cetera. The different possibilities, we assign a probability to those. And in general, they can depend on the covariates. So depending if I'm old, depending if my blood pressure is low, depending if I am educated, that can influence the probability of what treatment I receive. And in general, it can also depend on the actual unobserved potential outcomes that we assume exist. And then you'll see why this is important. So this treatment assignment mechanism, the difference for Rubin between an experiment and an observational study is that in an experiment, you control that assignment mechanism. You decide who gets what. It can be random, but you know exactly the process that led to receiving either a treatment or control. In an observational study, you don't know that process. You're trying to model it or estimate it, right? So if you're studying the effect of smoking on lung cancer, you don't know exactly how people sort themselves out as smokers or non-smokers. So you don't control that assignment. And Fisher, who invented the randomized trial, even said like, this problem would be trivial if we can put thousands of people in a trial at 13 and tell them you will be a smoker, you will not be a smoker. And then we just look at them through their lives. And at the end, we just compare them and we would solve the problem. But obviously we can't do that. So there's a big difference in observational versus experimental studies. And this is kind of what we're trying to understand. So to Rubin, the goal of the design of the study is to make the treatment assignment independent of the potential outcomes. So what does that mean? So formally, it's just saying, well, this quantity, right, the probability of being a smoker or not a smoker, we want to make that independent, right? So we don't want it to depend on the potential outcomes. Okay, we want that to just be depend on the covariance at worst. Okay. Let's consider the example of the perfect doctor. Okay, so the perfect doctor, what does the perfect doctor do? Well, he gives the treatment only to those that benefit from it. Okay, so most doctors are good. They're maybe not perfect, but when they give a treatment, they expect it to make your situation better, right? They don't want to worsen your situation. So let's assume that the perfect doctor, he has these metaphysical powers and he can look into the counterfactual worlds and he knows what are the potential outcomes and he gives only the treatment to those that benefit from it. Okay, so for example, this unit right here, when he receives the control, okay, let's assume that 1 means he has a headache and 0 means that he has no headache. So if you give him a placebo, he has a headache. But if you give him a aspirin or another treatment, he has no headache. Okay, so the doctor, he assigns the treatment, the active treatment to that unit because he knows that that will benefit him. And in the data, what you'll see is that this person has the outcome, no headache. Okay. So because the doctor can kind of peer into these counterfactual worlds, the doctor knows that by doing 1 minus 0, 0 minus 1. Okay, so the person goes from having no headache to having a headache if you don't give him the treatment. So the treatment reduces the headache. So we can say that the treatment effect is 0. Okay, you can minus 1. You can say it's 1 depending on how you look at it. But the minus here is just telling that it's reducing the headaches. Okay. And you can kind of do that for every person. So when someone is assigned the treatment, it means that they have the headache if you don't give them the treatment, but when you give them the treatment, they don't have the headache. Okay. If the doctor doesn't give the treatment, well, it's because either the person has a headache in both conditions, right? So for this person, the treatment does nothing. The person still has a headache, or the person already didn't have a headache, so why give them a treatment, right? Okay, so for these people, the treatment effect is just 0. Nothing happens. Okay, they stay the same in the counterfactual worlds. Okay, so obviously this is hypothetical. There's no person out there that can do this, but for the thought experiment, let's imagine we can. And in this scenario, you don't need to take a causal inference class because everything is easy. You can just look at these individual treatment effects and you know if your treatment is good or not. Okay, you don't need to do anything. Okay, so in this scenario, you can calculate the real average treatment effect. Okay, we assume that this is the full population of 6 people. You can just calculate the average treatment effect, and it's 1/2, okay? Minus 1/2. Okay, so kind of 1/2 of the population benefits from this treatment. You can see it like that. Okay. So that's the perfect doctor. He always does the right thing. He always cures. If he gives you a treatment, it's always to cure you. Okay? In practice, we don't have this perfect doctor. So what do? We kind of estimate the average treatment effect. So that's why I put a little hat on the expression. The little hat here. Okay, and I say that it's naive, okay, because at this stage of your course in causal inference, you probably know that doing this is not good enough, right? You can't just look at smokers, look at non-smokers, and compare cancer rates. Okay, that's not sufficient. But let's say we do it. We do this naively. Okay, we're in the pre-causal inference era. We don't know what we're doing. So we look at the perfect doctor's experiment, and we can't see the potential outcomes. We can only see the observed values. Okay, so we compare the treated, these persons, to the untreated. Okay, and we just compare the outcomes that are observed, right? Because we don't know the potential outcomes. Well, if we do this, okay, we get 0 minus 2/3, so we get a treatment effect of minus 2/3, okay? And remember, in this hypothetical scenario, there's no sampling variability. It's not just, oh, we are a bit off because we don't have the full population, there's confidence interval. No, this is just a systematic bias created by the perfect doctor, okay? So the perfect doctor, if he always gives the treatment to the right people, he will overestimate the power of his treatment, right? Because he will only see those that benefit from it. He will only give it to them. Whereas if we give it randomly, some people that will not benefit will be in the treatment group, so that will reduce the kind of estimate of the strength of the treatment. Again, this is a key insight. So the fact that we kind of overestimate, right? We think that more people benefit from the treatment, right? So there's a reduction in 2/3 versus 1/2. This is a systematic bias, okay? It's not bias due to estimation or uncertainty or sampling. It's just the assignment mechanism is not letting us estimate the treatment effect properly. Okay, so we don't want, in observational studies, we want to avoid this perfect doctor problem. Okay, we don't want the assignment to depend on the outcomes that we don't observe. We don't want the assignment to kind of be favorable to those that benefit and disfavorable to those that don't benefit, because this biases our estimates. Okay, and to make it a bit more concrete, so the doctor doesn't need to be perfect, okay? By simply favoring those that are more likely to heal, as any good doctor would, this will systematically overestimate the treatment effect, okay? So this is kind of the problem of confounding, okay, of the treatment assignment. Okay, so in formal terms, if the probability of being assigned to treatment depends on your potential outcomes, it depends on if you would benefit or not. For example, higher potential outcomes lead to higher probability of being treated, okay? Well, in this case, the probability of receiving the treatment is not independent of the potential outcomes, okay? We can't remove that from the expression. And this is what we call confounding in Rubin's framework, okay? So can we think of other examples of real life situations? So this is a perfect doctor. It's not really realistic, but Can we think of real life examples where your decision or your propensity or your probability of being exposed to a certain treatment or a certain environment or a certain factor depends on the benefits or the consequences related to being exposed to that factor? Okay. If we think about it, in science, that happens a lot, but also in everyday life, right? So imagine you want to understand if going to university increases your income. Well, probably people that go to university, they do it among other reasons because they believe it's going to increase their income, right? So the decision to go to university is related to what you think the outcome is. So we can't just compare people that go to university and people that don't, okay? Because they might be different for different reasons. Okay, so I'm sure you can think of other examples from your field where the decision to get exposed or get treated in the large sense is related to what you expect to happen from it. Okay? So this is the problem of confounding. And the solution, well, the solution is to make the assignment of treatment independent of anything that's relevant, okay? And this is one of the insights of modern experimental science is, well, one easy way to do this is literally using a physically random device, okay? So literally the fact that a coin falls on heads or tails is completely irrelevant of everything in the world. It's assumed to be perfectly random. So if this coin is deciding where you are going, either treatment or control, it cannot possibly be related to any outcomes because it's related to nothing. It's just a systematically random thing. Okay, so this is why randomized experiments solve that problem. And this is kind of the idea of Ronald Fisher in the 20s. There's obviously some precursors to that idea, but he's the one that really put it forward in full force. And after Fisher, the experimental science changed completely. Okay, it was randomization era. Again, randomization formally, again, the formalization is not really the important thing, but formally we can just say under a randomized assignment, we have this equality, okay? So the probability of being assigned to treatment or control does not depend on the potential outcomes, okay? And even if, we can even say that if it's completely random, meaning really just you come into the trial, we do heads or tails and we assign you, then in that case, the probability of assignment does not depend on your covariates either. It does not depend on if you are your age or your sex or whatever. Okay, but in some cases, like blocked experiments or other kinds of experiments, it can depend on your covariates, but that's not a problem as long as it's not dependent on your potential outcomes. Okay, so this is just a formal way of kind of summarizing all this in a very small mathematical expression. Sometimes it helps, sometimes it's just a bit abstract. It depends on your background. In observational studies, obviously we don't have that random assignment. So we can imagine that the doctor, I wrote perfect, but let's assume that, sorry, this doctor is not perfect. This is just a doctor. He doesn't know the potential outcomes, but he decides based on your covariates, right? He says, okay, this person is male, aged older than 60, with no history of heart problems, blah, blah, blah. So I should probably give him the treatment or not, okay? So if he looks at a patient profile given X, okay, obviously he doesn't know everything. He doesn't know if the treatment will be beneficial with certainty, but he can kind of look at your patient profile, and if in that profile, after it, the decision is essentially random, like not 50-50 necessarily, but it's kind of an intuition that's a bit random. Well, then the treatment assignment will be independent of the outcomes, but it will depend on the covariates, the characteristics of the person. Okay. And again, that probability does not need to be half. It just needs to depend on your covariates, but not the outcomes. Okay? If the doctor is working like this, okay, again, it's a bit hypothetical. The key insight is that he's essentially performing mini randomized experiments. So for a given group of patients that have certain characteristics, he's deciding randomly. So within that strata of population, it's kind of like a mini randomized experiment. Okay. And that's the key insight of the Rubin causal model. Okay, so if conditional on the set of covariates, the treatment assignment is essentially random, then it's independent of the potential outcomes, and we can estimate the conditional treatment effect by simply comparing the treated to the non-treated, and then averaging the results over the x. Okay, so for each value of x, so for each value of the covariates, we have a mini randomized experiment. We can estimate the treatment effect in each of those groups, and then we can take an average, and by a bit of math magic, we know that that average will be a good estimate. Okay? So that's kind of the way we should do in observational studies. Okay, we want to compare patients that are similar in the covariates that we think influence the fact that they receive treatment or control. And sometimes we think of this as balancing the groups on the covariates, okay, or making the groups exchangeable. Okay, so if the two groups are balanced on the important covariates, then the difference we see cannot be due to these covariates. It must be due to the treatment effect. Okay, so that's kind of the Rubin way of seeing the solution. And to do this, we can use a bunch of techniques that you probably learned in this course, right? Matching, weighting, stratification, regression adjustment, etc., to kind of help to achieve this balance so that we can unbias the estimate of the treatment effect. And the statistical properties of these techniques are continually being studied and refined. Okay, so we're still we know some things work better in different situations, and it's still evolving. Like there's not one way that solves all the problems and has all the like. We're still studying how these things work, and the more advanced things, or like targeted maximum likelihood and things like that. These techniques offer more promises on the statistical properties of doing this. But all this depends on the causal model being right. Okay, so having a good statistical process is worth nothing if your causal model is wrong. Okay, like you're just estimating the wrong thing. So it's important that you get the causality part right. So the Pearlian structural model, structural causal model, uses a directed acyclic graph. Okay, so a DAG, along with a set of functional relationships, so that kind of model the relationships in the DAG. Okay, so there's kind of two components. There's the visual, but underneath that, the structural component is this set of functional relationships. Okay, so you can use a DAG. You don't need to have a full structural model, but Pearl's thinking is always in terms of this full graphical and functional model that he puts together. Okay, so we have this DAG. Yeah, sorry, it's a bit blurry and small, but we have this X variable that we assume is the treatment. and we kind of think that it has a causal effect on an outcome. And sometimes we have other variables. So this one I called it S. Okay, and let's say in this case, S affects both the treatment and the outcome. And this is a classic case of confounding. So probably you've already seen that pattern. And the structural part, so the functional model that goes on top of this, is basically a model that says, okay, X receives its value by looking at S and a random error. Okay, so it's S plus a random error. Okay. The same way, so Y has two arrows going into it. So it has X and S. So it looks at X, it looks at S, and it plus a random error. Okay, so Y gets its value by looking at X, by looking at S plus error. And S in this model, it has no arrows into it. So S is basically just, we call it exogenous. It's just receiving its values through a random error process. Okay. So this is like a structural causal model. Okay, so you have a graphical depiction of your set of variables and their relationships. And we have a set of functions. And for the purpose of this presentation, I mean, it won't be super important anyways, but we will assume that, we will assume that the error terms are independent of one another. Okay, so uncorrelated errors, but that's not super important for today's talk. Okay. Okay, so for Pearl, when you have that system, he defines the causal effect differently. Okay, so for him, the causal effect is not a contrast of these two counterfactual potential outcomes. For him, the causal effect of X on Y is simply the distribution of Y when we intervene on X. Okay, so what is the distribution of different Y values given that we intervene to fix X at a certain value? Okay, so we'll call it little x. Okay, and he denotes this with the do operator. So I don't know if you saw it in this class, but this is something he invented. Okay, you never saw this in statistics before. He invented what he calls the do operation, which is kind of the formal way of saying that there is an intervention on X. And there's different mathematical things that you have to do to make sure that this makes sense. But let's just assume that it works. Okay. So the way he models this kind of intervention at X is to start by severing all the arrows that enter into X. Okay, so if we go, if we go here, right, when you do X, okay, you're kind of fixing it at X, so the impact of S is gone. Okay, X cannot listen to S anymore because you physically manipulated the system to fix it at X, so it's not listening to the value of S. And then you update your structural component, so the equations in the model, to propagate the effect of X through the model. And the way you do that is, well, X is no longer a function, it's just the value that you fixed it at. And then you propagate that, so you start, you put little x in your equation everywhere, and then you just update all the values, and at the end you can estimate the distribution of y. Okay, because you had the pre-intervention model, and then you can update it with the intervention, and you can recompute your things, and you can estimate the causal effect of x on y. So that's how he sees like a randomized trial for Pearl. is you're intervening on the variable, and then you're looking at how that modifies the outcomes. Okay? So when you're in an observational study, you can't do that. Literally, you cannot do the intervention. Okay? You cannot apply a do operation because you are not controlling the variable. Okay? So in general, what you do is you look at people that have the value set at smoking, for example, but you're not physically imposing that everybody smokes. Okay. So in general, physically imposing that everybody smokes is not the same as looking at the people who already smoke. Okay. That is kind of the difference. Okay. So an intervention is not the same as an observation. Okay. So Perl, to kind of make that problem soluble, to kind of allow us to work in observational settings, he developed the backdoor criterion that you probably learned also. That is a set of rules that you apply to your structural causal model. And this will help you find a proper adjustment set. We'll call it Z, that identifies the causal effect. Okay, so this is all jargon, but it's intuitively, what does it mean? It means that when people have the same value of Z, okay, the backdoor criterion tells you when you can see the intervention as being equal to just looking at the people that already have X. Okay. So it's similar in a sense to Rubin, where if you have the good set of variables to adjust, then you can kind of, there's no difference between experimenting and observing. Okay, you get the same result. So this is what Perl calls the identification of causal effects. So in natural language, within units who have equal values of Z, right? So intervening to fix X or observing that X is X is the same, okay? Provided that we're looking at people who have values equal Z, and Z is given by the backdoor criterion. And you can, there's an algorithm to do this. It's not, you don't even need to think. You can press a button and it's going to tell you what is the set Z that exists, if any, given your structural causal model that you posit to begin with. To estimate the causal effect, what happens when you intervene at X? What we do is we look at the adjustment set Z and we do a weighted average. Okay, so we weight by the probability of observing Z. And because the causal effect is identified, doing this or observing this is the same. So we can, this equality is licensed. So when we go from this to this, the difference is that in the final expression, there's no do operation. So all of this is observable. So we can just compute it in the data. Okay, so that's the formal way of looking at it, but it's intuitively similar to Rubin. You find the good covariates, you adjust for them, and then observing and intervening are the same.
And for a while, I think there was this competition. I think the competition for the RC, for this Rubin causal model potential outcomes approach was the graphical stuff. You know, was the DAG stuff of Judah Perl, and Perl's a great character, but I always found just the DAG stuff to be clutter, because it added something that wasn't essential at all. I mean, graphs are fine, but the DAGs, what, you know, with all their as soon as you get to something in experimental design, for example, split plot models or things like that, complicated, not just simple randomization, the whole thing falls apart. The whole simplicity of DAGs goes away. So why keep pursuing it?
So that's Rubin. So he doesn't really think it's relevant. So that's today, okay? But let's go back in time a little bit, right? So his position is essentially that this stuff is not useful, okay? Like it's just adding unnecessary complication to him. And in his kind of final textbook, I guess, that kind of summarizes all his approach. It's a great book, a bit abstract and mathematical, but so it's the Imbens and Rubin. He has one paragraph about Pearl, right? So it's kind of the same sentiment. Pearl's work is interesting. In our work, we have not found this approach to aid drawing of causal inference, and we do not discuss it further. And so he kind of just dismisses it and then doesn't talk about it anymore. And Pearl, on the other hand, he's kind of constantly talking about Rubin and arguing that his work is better and it's more important, and it's Rubin is just dogmatic, and statisticians, they should listen to Pearl. And probably in one day we will realize that Pearl was right all along. And that's kind of his point of view. And his main criticism is that his approach is not communicable, in the sense that nobody knows what this equation means. Okay? So remember, I showed you this equation. I said when the treatment assignment is random, for example, we say that it is ignorable. Okay, so that's a technical term. And he says nobody thinks like this. Okay, nobody understands what this means. So on the other hand, DAGs are very simplistic, they're very intuitive, so that's how scientists actually think. And we will discuss the problem called M bias. Okay, so this is kind of, it brings everything really in center, and they actually had debates. They sent papers to one another. So let's study that debate a little bit. Okay. So in 2007, Rubin just publishes a stat paper called The Design versus the Analysis of Observational Studies for Causal Effects, Parallels with the Design of Randomized Trials. And in that paper, he does the technique that I mentioned to you earlier about propensity score matching, and then even adding the covariates into the matched sample in the regression model to estimate these causal effects. And this is a study he did for a panel of judges in court. So it was this big thing. There was big committees involved in selecting the covariates. So it was a big, complicated study. And he's just trying to show how, in his mind, the important thing is modeling the treatment assignment, right? And to him, this is a matter of design. So you should do this, right? Select the match sample and everything. You should do that without looking at the outcomes. Okay? And in his case, it was easy because the outcomes were not available yet anyways. Okay? So they still had it to be collected. And this is like the main point that raised the debate. So he said that any covariate should be controlled for, namely by ensuring balance between treated and control groups, as we discussed. And he defines covariates. So covariates are variables that take the same value for each treatment for each unit, no matter which treatment is applied to the units. Okay, so if you take a aspirin or a placebo, it doesn't change your age. It doesn't change your sex. It doesn't change a bunch of characteristics about you. To him, these are covariates, and they should be adjusted or controlled for as many as possible. Okay. So for example, quantities measured before treatments are assigned. Okay, so these should be adjusted for. And this is largely adopted by at least a part of the statistical community. Like anything that happens before treatment is fair game. You can adjust for that, and you probably should, because it will help balance and it will give your estimators tighter confidence intervals and things like that. Okay. But the Pearl camp, here they sense an opportunity to disrupt this kind of establishment. Okay, so review just quickly of confounders. We talked about them briefly, but right, the confounder is a variable that creates a backdoor path between the treatment and assignment. And if we use the backdoor criterion, we can show that in this DAG, for example, if we adjust for the confounder S, the intervention on X or observing X is the same. So we can identify the causal effect. We can estimate it in our observational data. And a collider, again, you're probably familiar with this, right? So we have two arrows entering from the treatment and outcome. And this variable blocks the backdoor path. And it can be shown in the Pearlian framework that if you adjust for this collider, okay, you lose the equality, okay? So you're not, intervention and observation are different, okay? So you're creating a spurious association, right? Or you're biasing your causal estimate if you condition on a collider, as you probably already learned. And why is this important? So obviously, statisticians, they know this, okay? Maybe not in the language of Perl, but they know that you should not condition on the collider, at least in certain cases, right? So anything that is post-treatment, if we adjust for that, can obviously create bias, and statisticians know that very well. For example, when there's loss to follow-up in a trial, if it happens differently in both groups, but we only keep the people that were not lost to trial, this is a form of conditioning, and we're potentially biasing our estimate because the groups are different because of something that happened after the treatment. Right? And they're just an aside, but there's a great paper that maybe you know, right, by Hernan and the gang, right, that kind of shows that essentially all forms of selection bias can be thought as conditioning on colliders. Okay, so this kind of gives you instead of learning 200 different kinds of selection bias analogs, you can just always think of them as collider bias on a DAG. So for statisticians, anything before the treatment is good, anything after the treatment is bad. Okay, so that's kind of the general rule of thumb. And the aha moment for the Pearl camp is like, we got them, okay? Because in this case, if you have this exact DAG, well, this can happen before the treatment, okay? But you should not adjust for it, okay? And that is because it's a collider along this path. So this path is closed. It's the only backdoor path. So as a matter of fact, the causal effect of the treatment on the outcome, you don't need to do anything. You can just estimate it naively. You don't need to adjust. And if you adjust for this variable, you're actually creating bias. So in 2008, 1 year after Rubin published that paper, a guy named Ian Schreer, who's actually a scientist in my hometown of Montreal, he wrote a letter saying, hey, Rubin, did you consider this problem? What happens if you condition on this variable? You're going to create bias. So in this DAG, to make it even more like putting the statisticians in the corner, Z1 and Z3 are unmeasured. Okay, so you can't just say, oh, well, yeah, if I put Z2, I'm opening the path, but I can close it again by adjusting for Z1 or something like that. Okay, you're saying, no, these are unmeasured. You can't adjust for these. You can only adjust for Z2. So they say, well, Rubin, your method would probably tell us to adjust for Z2, but the backdoor criterion tells us that this would create a collider bias, and you cannot remedy the bias because Z1 and Z3 are unmeasured. Okay, so we got you. And what are you going to do? So to them, statisticians were wrong and Pearl's thinking revealed the truth. Okay. So Rubin replies, obviously, he sends back a letter and he kind of says, I don't really understand what you're talking about because I don't even use DAGs. So he kind of doesn't answer the question. He says, the letter uses notation and terminology entirely different from what was used in the target article, which puzzles and confuses me. Okay, so he doesn't understand. Then there's another guy, I don't know how to pronounce his name, Scholander. He writes in 2009, kind of trying to be the mediator. Okay, not mediator in the sense of mediation analysis, but mediator in the sense of trying to bring them together. So he kind of tries to help them understand each other. He puts notation and he kind of gives the presentation I gave in the past hour, just explaining both frameworks and how they can kind of reconcile. And then Pearl writes in and he kind of tells Rubin, no, Rubin, you're wrong. And then Rubin replies saying, well, anyways, this example is far too contrived to be of any practical importance. Why would you not adjust for pre-treatment variables and try to make the groups as balanced as possible? And in the final reply, he's really annoyed. Okay, and this is the first quote we got. So a few spicy quotes. The only design advice that I can garner from these letters is that we should ponder the possible existence of unobserved imbalances, okay? And then do nothing about some observed imbalances, not okay? The rationale for this implicit advice is the well-known mathematical fact that marginal independence between two random variables does not necessarily imply conditional independence between them given a third. Basically, he's saying this story of colliders is very trivial. We know about this. We don't care. Okay. So the letter seems to suggest that this fact has only been recently discovered as is important for causal inference and observational studies. I think that neither is accurate. And so he says, I don't really care about that collider stuff. It doesn't make sense. He says, time spent designing observational studies to have observed covariate imbalances because of hoped for compensating imbalances in unobserved covariates is neither practically nor theoretically justifiable. So in his mind, you should always balance on the covariates. He doesn't think that this M bias thing is really relevant in practice. And this is the final quote that I kind of gave in the beginning, right? To avoid conditioning on some observed covariates in the hope of obtaining an unbiased estimator because of phantom but complementary imbalances on unobserved covariates is neither Bayesian nor scientifically sound, but rather it is distinctly frequentist and non-scientific ad hocery. Okay, so this is the DAG that they're discussing. And if you use this tool, it kind of does the backdoor deseparation stuff for us, so we don't need to worry. But so the model implies the following conditional independencies. Okay, so this model is saying that all these independencies exist. Okay, so in other words, if you do a regression of A on B, the coefficient should be exactly 0. If you do a regression on A on D and E, the D coefficient should be exactly 0. If you do a regression of B on E, the E coefficient should be exactly 0, et cetera, et cetera. Okay, so these are a set of very strong assumptions. Okay, so we have to keep that in mind. And each of these can be attributed to a lack of arrow between two variables. Okay, so if I add an arrow here, we lose some of these independencies in the data, okay? Because we're saying, oh, well, the coefficient here would not be 0, right? And if we, right, we can add arrows and we see this, the set of conditional independencies here is smaller and smaller, okay? So the way I think of it is you have a full bag and every time you're removing an arrow, you're making a strong assumption, okay? So I'm not saying like that I don't think the M bias is real, but we just have to keep in mind that it's an extremely strong set of assumptions when you're saying, oh, this is the system that explains the causality between my variables. So if we add one here, right, we create a backdoor path, things like that. Okay. So if we give Rubin the benefit of the doubt, because he never really addressed the problem, he kind of dismissed it, and we saw he was a bit arrogant and condescending even. I think the main thrust of his argument is that assuming that this exact set of conditional independencies is not a good reason to not adjust for pre-treatment covariates. Okay? I would say that's his main argument. Okay. Obviously, he also dismisses the whole Pearl work, but that's sometimes intellectuals are like that. So in other words, M bias is a theoretical curiosity, but not a practical concern. Okay? So isn't it all just conditional independence? So in 2009, in an unpublished technical report, Pearl writes, while finding a pure M structure totally free of bias may indeed be rare in practical studies, not unlike the rarity of finding any conditional independence, cases containing local M structures are abound. And so he's saying, yeah, it might be rare, but maybe not that rare. But to me, this is just a contradiction because he says, yeah, it's very rare to find conditional independencies, but we just saw that the M structure is in fact a large set of conditional independencies. So does he think it's rare or not? I'm not sure. Because I think he's trying to argue, well, Rubin, your conditions are also conditional independencies and they're very hard to find. So he ended up in 2022, so very recently, he was interviewed and he continues to talk about this, saying that, Rubin refuses to acknowledge the M structures, he's dogmatic. So he says, Rubin's potential outcome framework became popular in several segments of the research community. These researchers talked conditional ignorability, which is the assumption that we discussed earlier, that the assignment does not depend on the potential outcomes. To justify their methods, though they cannot tell whether it was true or not. So conditional ignorability gave them a formal notation to state a license to use their favorite estimation procedure, even though they cannot defend the assumptions behind the license. And then he continues. So he says the main thing, they can't tell if their assumption is true or not. Okay, I think that's a fair point. But I think we can say the same of a DAG. Okay? I'm not sure how we can tell if a DAG is true or not. In both cases, we have to assume that it's true to do something. Okay, so you can kind of test the DAG, but you kind of have to assume that it's true and the assumptions behind it are true. And I think that's kind of true of any causal inference method. It's one of the big discoveries of causal inference. It's that it all relies on sets of things that we can't verify. We have to assume and use logic and scientific knowledge to gain confidence or plausibility in the assumptions, but we never know if they're perfectly true. Unless we use randomization is like maybe the only case that works. Okay, so more spicy quotes. So in the potential outcome framework, problems are defined algebraically, blah, blah, blah. These type of assumptions are too complicated to interpret or verify by unaided judgment. In the structural framework, on the other hand, problems are defined in the language in which scientific knowledge is stored, causal graphs. But I think this is funny because he also in the same text, he says, like, I have to fight so much for people to understand graphs. But now he's saying that it's the natural scientific language. So is it natural or is it something you have to learn? So kind of to summarize for my take, I think to some degree they're both preaching to the choir, right? It's like their work, they spend their life doing this, they're very proud. I think DAGs are extremely useful, but I think the counterfactual thinking is very essential to causal inference. Like I don't think we can kind of forget about that. So in a sense, they're so useful and intuitive that their apparent simplicity can be misleading. I always use them anyways. I think they're very useful. And I'm sympathetic with Rubin, but I also like to use structural causal models. Sorry, I'm going a bit fast because it's over. And it's possible to kind of make a unified version of both frameworks, but it's pretty complicated. I haven't read all of it, but there's Richardson and Robbins that propose a unification. It's 148 pages of mathematics, so probably most scientists don't care. But maybe that's kind of the way forward where we kind of make the best of both worlds into one framework. But who knows?